Hi, Hugh. Thank you for joining this follow-up session.
Hello?
Yes, I have a few questions to follow up your talk. And first of them is exactly about this figure, about what was exactly shown in the figure by Yegor over 2018. So please tell a few words.
Okay, well, these are reconstructions, I believe, done in this paper by Yegorova et al. Of the total solar irradiance and its comparison with models. The two panels there showed different model comparisons, and the vertical scale is the important thing here. It's watts per square meter. So this is the excess irradiance due to the phenomena that are being modeled. And the big dip on the left at 1700 is the Maunder minimum. So relative to the Maunder minimum, where the plotting here makes things match, the excess above that is the total solar irradiance at other times. And the importance of this probably is that the Maunder minimum is pretty strong, a pretty strong effect of 5 watts per square meter. That's on the order of 0.5% or a few tenths of a percent. So probably detectable on the Earth, and so Jack Eddy, when he pointed out this association between the Maunder minimum and the Little Ice Age, probably was right. And the people who would say that the TSI is not varying by very much over the hundreds of years that we can do this kind of extrapolation are also pretty right, except for the Maunder minimum, it looks pretty stable. So the reason I showed this is simply because this particular paper deals with an astonishing array of inputs, including radioisotope, cosmic ray data, and other kinds of factors, including microwave imaging. In this case, it was ALMA, but the wonderful array in Owens Valley is also a possible source of this kind of thing. So this is atmospheric structure, the physical nature of plage and solar activity is what's being modeled here. So I think that's sort of the story. I hope that is explaining pretty well. I like this because it's so broadband and Catholic in its approach to the research.
Yeah, I think I believe now it's clear because during the talk it was only captions in the panel itself, so it was not immediately clear what is what, but I think now it's fine. Another question was to clarify what do you mean about what is limb showers, and is it solar limb or earth limb? So just if you clarifying.
Yes, that's a new thing. That's something that not that I invented, but something that I'm pointing out, which has hardly been studied and which may have very interesting consequences, and that is cosmic rays, very high energy charged particles, the galactic cosmic rays, for example, or solar cosmic rays of higher energies, can penetrate the solar atmosphere tangentially. If they're high enough energy, they're not deviated by the magnetic field. They can just do a grazing incidence interaction. And if they go through the dense atmosphere at the photosphere, where the column density vertically is a few grams per square centimeter, actually the real photosphere, if they go through sideways in that region, the equivalent of the extensive air shower will develop. There will be an initial nuclear reaction. A particle, a primary proton will strike a nucleus and make a secondary particles. These particles always include lots of pions. The neutral pions can decay into 2 gamma rays each. The charged pions can decay into mu mesons, which decay immediately into electrons or positrons, which then emit bremsstrahlung. So these high energy photons, either direct pi zero decay or bremsstrahlung, can also do pair production. This is a part of the shower development, and the pair production leads to more positrons, more electrons, more photons, and so this cascade really amplifies the X-ray, the lower energy bremsstrahlung spectrum, and it's in a very flat spectrum. So the air showers occur on any object that's exposed to radiation in space. The Earth has a very bright limb, as seen from space. Because of this, Venus would have a very bright rim with an annular structure around its limb, and also the sun. And the sun is very interesting from this point of view because this may be the place where these Fermi-Lat long duration gamma ray events are happening, and so this may play a role. And it also inspires us to think about something else which is not very much thought about in solar physics, and that is that these products, and you would also get products from cosmic rays or high energy particles going back into the sun directly. There are products that are secondary products like neutrons. So these neutrons can come back out of the sun, scatter back out thermally, and then get into the solar atmosphere and decay and become protons and electrons. And these are it's a necessary consequence of that there are kind of radiation belts in the solar corona secondary to this process. It's called CRAND, or cosmic ray albedo neutron decay, and it's the main process by which the Earth's Van Allen belts get populated. So it's happening on the sun, but as far as I know, nobody's ever talked about it. So that's the air showers is an extension of this air shower business, limb showers.
Okay, it's really a very interesting note about tangential.
Tangential, yeah.
Tangential.
Also, another interesting aspect of this, and if you just want to talk about this, is so I asked the world's leading expert on this at this meeting that I'm at. This is Igor, his name is Moskalenko, and he's a part of the Fermi team. And so I asked him, do cosmic rays hit stars? So it's kind of a dumb question. Of course they do. But they don't hit them very often because stars are few and far between. On the other hand, cosmic rays in the galaxy go very fast, and they sample the galaxy many times as they scatter around. And so this process of limb showers is working in stellar atmospheres all the time just as well. And so the significance of that is that the shower products may include exotic species because of the nuclear reactions that are taking place, things that wouldn't be produced as the cosmic rays interact in the interstellar medium, but are produced in stellar atmospheres. So I don't think there's much literature on this. I think it's quite an interesting process. I think that.
Okay, I see. Thank you. And I had a question, not surprisingly, question from my colleagues from Solar Radio Group. What is your opinion about potential role of radio domain in solar studies?
It's dominant, and if I didn't mention it, it's also because I'm such a firm believer in radio astronomy, and I sometimes forget that everybody isn't the same way. And now that I'm reminded, I will remember that many graduate students do not know the difference between a type 3 burst and a type 2 burst. So, and the Owens Valley, EOP says, is the best facility there is dedicated for solar microwave observations in particular. So all I can do is say, sorry not to emphasize that aspect of things, only 45 minutes, and I will try not to repeat that mistake again. I actually made the same mistake at the American Astronomical Society meeting in January. Dale Gary was in the audience. I just blithely talked about something interesting without mentioning this aspect of it, which is important. And Dale afterwards chided me about this. He said, "Hugh, you've forgotten us again." I only forget you because you're so good.
Yeah, it's understandable given 45 minutes talk, and from the same perspective, maybe you feel you missed something important, you want to emphasize again something, so you have a few minutes to do so right now.
So there, in the context of the long duration gamma ray events, this is a major aspect of the limb shower development that I talked about in the second half of the presentation. There's a very characteristic microwave signature, which I call the Frost-Dennis phenomenon. This is because Frost and Dennis published a paper on the first example of this kind of thing in 1971, The event that they observed was 1969, and it was characterized by an extraordinarily close match between the microwave time profile and the hard X-ray time profile, and several other aspects of this. The microwave spectrum had a very low peak frequency, and it was smooth, not impulsive. So the event lasted 10 or 20 minutes. Another characteristic was the very, very flat hard X-ray spectrum, means a very, very hard electron spectrum. And so these things are all quite different from the normal behavior of a solar flare impulsive microwave hard X-ray kind of signature. It's a different thing, quite a different thing. And so that's why I think giving it a separate name is good. And Ken Frost is an old friend, and Brian Dennis is a young friend. So why not call it for their discovery? Now, and nowadays, we can link these directly to these gamma ray events observed by LAT. Earlier, there were examples observed by EGRET, but now there are 30 or 40 examples from this beautiful cosmic gamma ray observatory, the Fermi satellite. And it turns out that the Frost and Dennis events, I think, are a substantial part of the phenomenology in these interesting gamma ray events. And something like EOPSA, the observations at EOPSA are ideal for characterizing, for imaging and characterizing the spectroscopy of these events. I don't know if there are any examples yet in the archive, but there was one on the September 10th, 2017 event. So I suspect that event and its analysis, I'm looking very much forward to presentation of the Owens Valley results on that in particular.
Okay, thank you very much, Hugh. I think that's it for our follow-up session. And let me stop the recording and thank our potential speakers, listeners, and watchers for listening.
Thank you.
Mm-hmm.